Welcome, listeners, to the second episode of Semi-Doped Podcast. I'm Austin Lyons of Chipstrat, and with me is Vic from Vic's Newsletters. We write about semiconductors on Substack, and now we have a podcast. Today, Vic is going to tell us about 5 cool things from the IEDM conference and why it matters. So over to you, Vic. What's IEDM?
Hey, Austin. Yeah, IEDM. Yeah, that's a short for International Electron Devices Meeting. So this is a conference that I went to in December 2025. And it's a conference that's entirely dedicated to transistors, optics recently, and a whole lot of stuff like about how interconnects are made, everything about transistor devices, memory, all kinds of fancy things like magnetoresistive RAM, ferroelectric RAM, anything you can imagine that's like even 5 or 10 years into the future. Very exciting place.
It's cool. Interesting. So is it like transistor physics type stuff, or are like circuit design folks there?
Yeah. It's actually transistor design. Okay, so that's like the key focus of this conference. There's a lot of like chemistry involved, and there's like a lot of material science involved. So this is like the actual core transistor devices that are being made. The circuits version of that would be the solid state circuits conference that's going to be held in February 2026. That's a nice conference to go to. I attended that last year, but this is just core devices.
Gotcha. Cool. And so why should our listeners care? Why are we talking about that today?
Yeah, so all the stuff that we see in transistor land, like, Intel's 18A or 14A or, TSMC's newer nodes, all of that starts at conferences like this. And all of what they launch into production eventually starts with technical discussions at research conferences like this. So you have like people from all the major foundries show up to these things, and they show the kind of projects they're working on 5 to 8 years into the future. So it's a really good place to go visit so that you get an idea for really what's coming down the pipe, like far out there, and it gives you really good insights into what technology cares about, what people care about, and what it takes to design something that is actually useful in the real world. So it's a research conference. It's highly technical, but the people there are very interesting.
Gotcha. Interesting. So as an engineer, it gives you a sense of like what's coming beyond the current set of technologies that you're using. And maybe for investor type audience, it's a glimpse of what technologies the future might hold, which of course they could think about with respect to what companies might be interesting looking 5 to 8 years ahead.
Yeah, exactly. So in conferences like this, if somebody asks me, I always tell them, always sign up for like the tutorials or short course sessions, because they take you from a reasonably basic state to almost cutting edge in like an hour and a half in a single talk. The technical sessions can get quite intense because they are given maybe half an hour to, show their absolute cutting future thing that they're working on. That's like a little much, for the general audience, unless you're really working on this stuff. It's kind of cool to see, but really the tutorials and short courses are amazing because you can go through the entire history of certain devices just by attending this for 1.5 hours a session. And it's usually the first 2 days before the main conference starts. So even if that is there, even if that can be attended by a more generic audience, it's actually worth it.
Nice. Awesome. That's a good pro tip. I didn't realize that you can go essentially get up to speed. And then when you sit in to those talks, they might just be right at the cutting edge, and you might essentially lose interest after 5 minutes because they've gone so deep into the weeds that you check out.
Yeah.
But the short course and the tutorials are actually sort of a great place for a lot of people.
Yeah, it is. Yeah.
Nice.
Cool. Highly
Makes
recommend
sense.
it.
Awesome. All right, man. So what is the first cool thing that you saw at IEDM?
Actually, I have a precursor to the first cool thing. I have like the 0.5 cool thing.
Okay.
So before one of the sessions, I was just like hanging out, and I ran into somebody from semi-analysis, so we were chatting. And then we met this person who is a very prominent technology person at a very prominent foundry. And they asked me not to say who or, which foundry, so just because they want to leave me out of it. But it was such a fascinating talk because I never imagined that I would attend one of these conferences. And like I was saying, the people are so interesting who you run into, that this person was actually part of a technology pathfinding team at a major foundry, right? So this person's major role is to find out how to make the transistors that we would use 10 years from now. And it was very fascinating to see how they think about this because, you probably want immediately work, a transistor that works immediately, right? Like you want all the good properties of this. They don't look at it like that. They're like, they invert the problem on their head. So what they do is they're like, out of the 20 problems that I will run into in developing this fancy transistor 10 years from now, what are the biggest blockers? Like there are some of them that are known, so they don't even touch that stuff. So when somebody asks for this, very basic, almost glaring absence of data on something, they say, oh, yeah, we know how to solve that problem. So we're not going to look at that at all. So we're going to solve what we think are like absolute blockers where this technology will not proceed unless these problems are solved. So this is the kind of thing they look at. And they look at manufacturability at scale from a very, very early point in the process of making transistors. So you would think that it's something like, we just make this transistor and figure out later whether you can print billions of them. They do not think that way at all. They think about manufacturability from the very beginning, even if it's 10 years out. It's very fancy. And it was nice that I got to talk about this kind of stuff for like an hour where everybody else had gone into their sessions and we're listening to the talks in the empty hallways. And I've got this, head of this person at this major foundry explaining to me and the guy from semi-analysis how transistors work. I'm like, how does this happen? This is ridiculous. But this is why. Yeah, this is why you're going to conferences. You never know what happens. You don't know what you don't know, kind of thing. That's why I love
totally.
it.
Yeah, just to go and get access to talk to people. And you can learn so much if you can just get face to face with the right people.
Right.
Definitely.
Right. Now we can go into the first cool thing I saw because I thought I should just mention that because I'm still kind of stoked by the whole experience.
Totally.
Yeah. So interestingly, in every conference, the organizers do one unique thing, and when you attend a few conferences, you start to see the pattern. They keep some of the most interesting talks towards the last day. And the reason they do this is because they don't want you to leave after the first 2 days and then go check out the local eateries, right? So they make sure to keep some of the interesting talks. So what I'm going to talk about first is like actually what happened on the last day. So they had a session called Silicon Photonics for Energy Efficient AI. And so I was like, oh, I've got to attend this because every major conference now is going to have a significant portion of it dedicated to silicon photonics. So this is an increasing trend that we're going to see going forward. Tells you how important this topic is. But one of those talks was actually from NVIDIA. And obviously, you can imagine if it's from NVIDIA, then everybody's going to pile into that room. It was packed, like people were standing on the aisles and all that. And essentially, they were just kind of explaining what kind of networking is going to be used and where optics fits in and all that. So it was nice. But the one big takeaway I had from the whole thing was that for the next generation of the Kyber Rubin Ultra racks, that optics is still too expensive for scale up. That was the key takeaway from this because they had a slide up there that says like, okay, if you have like 200 gig lanes and 8 of them running a 1.6T interconnect, and if that's running, let's say 9 watts, which is kind of reasonable if you think about like a co-packaged optics system, because you've done away with the gigantic DSP that you have to deal with in optical transceivers regularly that sucks up 20 watts of power all by itself. So now you drop from something like 30 watts overall from optical transceivers to just 9 watts or so with co-packaged optics. And that's the whole allure to co-packaged optics, the lower power consumption. You're spending about 5 picojoules per bit. And so if you translate this to a Rubin Ultra rack, it seems that it would take up about 20 kilowatts per rack. This was what was on the slide. And they also had a dollar value to associated with it, which says that at 5 picojoules per bit and 20 kilowatts, the cost to run this would be like $400,000. I calculated that to be about 5 cents per kilowatt hour. I don't know. I don't know exactly how the money part of it was calculated. It was just on the slide. But anyway, I think their point is that even 200 kilowatts is a problem uh, at a rack scale. So they were like, no, we want to use copper as much as possible. I mean, we've heard Jensen say this before too. Copper is where it's at. So optics is nice, co-packaged optics is nice. I'm sure we'll get better reach out of it, but people just want to stay optics as far as they possibly can. That's my takeaway. What have you heard about this whole scale-up thing?
Nice. Yeah, that's a good takeaway. Well, and it's very timely because a lot of people are asking, and I know you've written about it on your newsletter. When will the industry transition to optics for scale up, and what's going to be the driving factor? And so I guess that's one of my questions for you. You said, well, wow, there's still a lot of power that is consumed there, but there's cost was very significant. Is it what's too prohibitive right now? Did you get from that talk? Was it the cost angle or was it the power impact?
I think the key takeaway from what I heard was 5 picojoules per bit isn't good enough because it translates to a lot of power.
Yeah. Yep.
If you look at active electrical cable, we are at about half of that.
Gotcha. Yeah, and that makes a lot of sense because power is the sort of the ultimate constraint, not money, right? So it feels like if the power was acceptable at this point, and the cost wasn't quite there, that some people might jump over that hurdle and not be too concerned about it. But definitely, if you can only find so many megawatts of power at your facility and you want to instantiate or install a ton of new Rubin GPUs, it's all about power. So whatever you can do to save as much power as possible so that you can run even more compute, that seems like the driving constraint right now.
Yeah, and the other thing I want to add to that is that do we really believe that 200 gigs per lane and 1.6T is not possible with copper? Because if you look at Marvell's Alaska ADSP, it can run 1.6 terabits per second. Of course, I don't know exactly to what reach. They claim it's about like 5 to 7 meters, which should be okay. But then you've also got this other thing like micro LEDs that's, maybe useful. We don't know. Nobody's really deployed micro LED as an interconnect technology, but it seems like it's like lower power and less expensive than going to co-packaged optics right away for even scale up. I want to see what happens with micro LEDs for scale up. That's something I want to look into in depth for the newsletter as well. So it's in my plan to do. But yeah, there are a lot of options before we really have to hit optics as the only way forward. And I think people are going to be looking for any and all options before going optics.
Yeah, it definitely sounds like at the 1.6T generation that copper is still the way to go. Active electrical cables. And, the nice thing is NVIDIA is cramming more and more GPUs into a rack. So to scale up, you don't have to reach as far. So even if your copper, as the speeds scale up and your reach shrinks, well, guess what? That reach can still reach quite a lot of GPUs. So it definitely makes sense that for scale up, it's still copper for a while. But it will be interesting to see where this inflection point is as we'll continue to track this, and where optics makes sense for scale up.
Awesome. Let's go to number 2.
Sounds good.
The next thing was about complementary FETs and the progress, for digital devices in the future and logic. So for anybody who's not familiar with complementary FETs, I'll give a quick introduction as to how we kind of got here. In the beginning, we had planar FETs. This is, back in the 1990s or before that, where you could only control the transistor gate from one side. And so the channel was kind of, uncontrolled as it got smaller and smaller. And basically sometime around 2005, the Dennard scaling kind of ended, and the subthreshold leakage was too high, and transistors were leaking too much current when they were supposed to be off, and it just didn't work at that point. So the industry transitioned to like FinFETs, which means that your gate, instead of looking like just controlling from one side, it looks like a shark fin where you kind of control it from 3 sides, and that gives better control over the channel and lower leakage as you scale it down to smaller factors. And then today we've kind of gone into the gate all around, where you can surround it on all 4 sides and control the channel completely. And that's what, say 2 nanometer processes and below are going to be gate all around. Now, the problem with gate all around is still you've got an NMOS transistor and a PMOS transistor, which is what makes up for CMOS complementary, because you've got an N-type and a P-type MOSFET together, and you need both together to make all these circuits work. They're side by side. So that still takes up too much space. They're really small transistors, but they're side by side. Now, complementary FETs is the way of asking, what if we took those gate-all-around FETs and put them one on top of each other so that, we could build skyscrapers instead of, single-use, single-owner homes or whatever. And that way we can cram even more transistors into a, smaller footprint and get even more chips and transistors per unit area. So that's where complementary FETs are supposed to be going. We will likely see complementary FETs come out around the 0.nanometer node, or 7A, if you want to call it 7A. Don't know. At this point, it doesn't even make sense to call it like conventional node names anymore. But
Right.
if you want to compare it to 14A, which is like 14 angstrom, we're looking at a 7 angstrom technology that would kind of use CFETs.
Yeah, we almost should just switch to naming it like CFET version 1, CFET version 2, right? Like gate-all-around version 1, gate-all-around version 2, that kind of thing.
Yeah. So it's far out there. And so the one thing that TSMC has been steadily showing over the years is that in 2023, they showed basic current voltage relationships of a CFET. So which means they show an NMOS on top and a PMOS below. And there are some reasons why. I'll mention very shortly why this NMOS is on top. But then they showed basic current voltage relationships. So you kind of see like the typical curves you see for an NMOS and PMOS device. This is the basic step. You're going to show that the transistor works as a transistor should. So the next step in 2024, what they did was, obviously, when you have like an NMOS and a PMOS, literally the first thing you do in digital circuits is you build an inverter out of it. You put an NMOS and a PMOS on top and you hook them up, and then you put a 0 input, it gives you a 1 at the output. And this is like literally the first thing you do. So that's what they did in 2024. And in 2025, actually, it was kind of a big jump, honestly, because what they did was make a ring oscillator. And what a ring oscillator is, you take these inverters, which has an NMOS below and a PMOS on top, hooked up together, and you put like 101 of them together. And when you do that, what ends up happening is that it's basically acts as an oscillator. And the outside, at the output side, you see basically a square wave when the oscillator is started up. And usually the oscillating frequency for such a ring oscillator with 101 stages is quite high. So they usually go on the output side and they divide that frequency down so that they can actually measure it with like lab equipment. So the thing is, why ring oscillators? So ring oscillators are a perfect measuring vehicle to estimate what the delay is through a transistor. Or in other words, how fast a transistor is. If the delay through the transistor is really small, then the oscillation frequency would be much higher, and which means the transistor operates much, much faster, right? So a ring oscillator is really a fundamental circuit. The moment you build an inverter, the next thing people do is put them together, make a ring oscillator. So this is the next logical step. It was fancy to see, actually. There's a lot of engineering that goes into it. I mean, I can't even begin to say how complex something like this is. It requires even new material inventions because you want to isolate the NMOS on top from the PMOS below. So there's an intermediate material that's very important, and there's like a lot of innovation in just the material that separates the NMOS from the PMOS. So there's all that kind of stuff. It's kind of insane. And they put, interestingly, the PMOS down below because apparently when you squeeze the PMOS device by putting an NMOS on top, its mobility improves. And, when you strain it, somehow it conducts more holes. Okay. So they decided they'll put the PMOS down below and the NMOS on top. So you can get better performance of this way. But again, this is so far out into the future. Nothing is set in stone. If they find a better reason to put NMOS below, they'll do that, So it's very, very far out, actually.
Gotcha. Interesting. So zooming back out, so CFET is sort of the next thing. We went FinFET and then essentially ribbon FET, and CFET's next. And over the last couple of years, we went from just seeing like hey, look, we made this and it has the type of IV curve you'd expect, to, hey, check it out, we can make an inverter, to now we can make a ring oscillator. So we can make lots of these, we can connect them all together, and then we can measure intrinsic properties of the transistor with this oscillator circuit. And then you're highlighting that in doing so, there was actually a lot of innovation because we went from having the PMOS and NMOS transistors side by side, which takes up a lot of die area, to stacking them, which lets you shrink the footprint of the transistor or the pair. But it actually required new sort of research and development techniques to actually be able to stack them, to have it work, to be able to probe them. All of that's very promising. So do you have any expectation of what we might see next year?
That's a good question. No, actually, I have no idea because I'm not sure what they're going to do next with this. If you had asked me this last year after I saw the inverter, I would have said ring oscillator.
Yeah.
But maybe we could do more such building blocks around. Maybe we could see some other simple circuits. I really can't think of anything. But I'll tell you what, it's going to be a long way before we can see like a GPU built out of this stuff with like billions and billions of transistors. It's going to be some time before that happens. So don't hold your breath on that one. It's going to be a while.
Gotcha. Very early here. Do you expect that they'll stack more of these CFET on top of each other and keep going in that third dimension?
That's a really good question. I don't think we're there yet, but
Okay.
I'm sure we will be in 10 years. So if I'm attending IEDM in 10 years from now, that's what we'll be talking about for the next 10 years.
There you go. Check back on the 10th season of Semi-Doped Podcast, and we'll cover that.
By the way, one concluding note before we go to the next interesting thing of IEDM, I just want to wrap up this with one thing. So you remember the important person I spoke to that I mentioned earlier in this show? I asked that person, okay, you've been doing this a long time. From where I'm at, we've gone to like 1 nanometer transistors, and I asked them, do you have anything left to do in transistors, or now you're stacking them up? Are you done? Like, is there anything left to be done? A person says, I'm just getting started. I have 20 years ahead of me, and I've been doing this for 25 years behind me. I still have 20 years of transistor innovations ahead of me, so don't you worry. There's plenty ahead. I'm like, that's amazing.
I love it. I mean, I remember when we were in undergrad, people were talking about the end of scaling and that we were just going to hit a wall. And so even being here now, talking about 3 dimensions and CFET's pretty interesting, but it's awesome to hear from someone in the weeds that they're just like, we're just getting started.
Yeah. Cool. Let's go to number 3.
All right. What's next?
So this is a talk I heard from SK Hynix about a Penta-level multi-site cell. Okay, this is for NAND flash memory. So let me explain what all that means, because literally I had no idea until I attended the talk myself, and I was like, I had to educate myself quite a bit to get to even understanding what this is. So first of all, I must preface this by saying that this has a lot of potential to disrupt a lot of stuff in the SSD world and NAND world, flash memory market. And I'll tell you why that is, again, at the end of this little explanation as to what this is. So we can revisit and, the point as to why this is so important. Okay, the first thing I should say is how NAND flash actually works, because without this, nothing I'm going to say is ever going to make sense, right? So the way it works is that, think of a regular transistor. You have a gate, a source, and a drain. These are 3 terminals of a transistor. You could argue there's a 4th, but let's not confuse anything. Now, instead of a gate, you put another kind of gate on top of that gate, okay? Now, you could call it a second gate, or more commonly, it's a layer of silicon nitride, and it is a charge trap layer. The function of this layer is just it traps charges and holds it, and when asked to release it, it releases charges, right? So now, depending on whether the MOSFET holds the charge in a trap state or it doesn't hold the charge, you can kind of say that the transistor is holding a 1 or a 0. Okay, so that's how NAND flash works, basically. So you have these charge traps inside, and it traps it or releases it. Now, every time the charge is trapped within the MOSFET, its threshold voltage changes. So threshold voltage is the amount of voltage you need to turn on a transistor. So before the charge was trapped, let's say you had a voltage at the transistor, it was on and current was flowing through the transistor. Now you trap all this charge into the transistor, and now it turns off because its threshold voltage has gone higher, which means the voltage you were applying is no more enough to turn on the transistor, right? So now how they determine whether the transistor is a bit 0 or bit 1 is that they measure this threshold voltage in some way. Okay, so they measure whether it's a high threshold voltage or a low threshold voltage. So you can tell whether the NAND cell is holding a 0 or a 1. So that's the fundamental way. Now, the problem with this approach is that there is only one bit that can be stored, a 0 or a 1, with this kind of a single level cell, because either it's low VT, low threshold voltage, or high threshold voltage. So now people say, okay, that's terrible. I mean, I want more, data density. I don't want to store 2 bits with one transistor. I don't want to store 1 bit. I want to store 2 bits because I can get more data density out of a single transistor. So they're like, okay, now how do you get 2 bits? Like, okay, like why don't we just push more charge into the cell so the threshold voltage shifts even more, and maybe push even more so you can, like, now you can get 4 threshold voltages, corresponding to 2 bits, a 0 0 threshold voltage, 0 1, a 1 0, and a 1 1 threshold voltage. So now you have what is called a multi-level NAND cell. You have 4 threshold voltages that can hold 2 bits of information. Right? The transistor hasn't changed. It's the same thing, literally the same physical, but now you store double the number of bits, right? Now people have taken this to the limit, right? Today you have quad level cells, which means a single NAND cell can store 4 bits of information or 16 states. That's a lot. So it gets challenging at this point, and I'll tell you why that is. The thing is that as you add the number of threshold voltage states, it becomes very difficult to keep them fixed, because every time you take charge in and out of the transistor, it destroys it just a little bit. And when the transistor gets destroyed just a little bit, its threshold voltage changes. Now you can imagine you have 16 threshold voltages, all slightly moving here and there all over the place. Now, how do you decide which state is stored in the cell if all those 16 threshold voltages are moving as the cell degrades over time? Now, that is the problem with endurance and flash memory. As you keep taking charge in and out, you degrade it and you shift these threshold voltages. And not only that, they become very sensitive to temperature, because temperature shifts these threshold voltages around. So it makes it very difficult to use higher level NAND cells like this. And the other thing is that in order to determine what threshold voltage there is, it takes a lot of effort to set the right voltages to extract the right information from the cell. It takes a long time to do that. So latency becomes higher and higher as you stack the number of levels in a cell. So if you want to store 4 bits to a cell, it takes a lot more latency. Endurance gets worse. However, you have extremely amazing capacity, right? Okay, now nobody stops with 4 level cells. Now you're going to go to 5 level cells with 32 threshold voltage states. Just think about that. It's nuts.
Wow.
Like, it's a lot of states. And it's very difficult to do. This is still in research phases, and that's where SK Hynix comes in. And what they did was interesting. Like think about 32 closely spaced threshold voltages. It's a nightmare. Okay, it's going to change with time and temperature. Programming it is a nightmare. So they're like, okay, I'm going to literally break this transistor in half. Okay, and I'm going to say the left half of the transistor is going to have 6 threshold voltage states, and the right side of the transistor is going to have 6 threshold voltage states. And the combined state of the NAND cell is going to be what state the left half is and what state the right half is. So immediately you get 6 times 6, 32, 36, different threshold voltages, whereas you need only 32 to create a 5-level cell, right? Now, the beauty of this is that for every half cell, you have only 6 threshold voltages. So the endurance and the latency would be something between a 2-bit NAND cell and a 3-bit NAND cell. So it'll be faster than a TLC NAND while having the endurance of maybe a multi-level cell. This is fantastic because you got even better density without trading off any of the latency or endurance downsides by just breaking the transistor in half. So this is what they call their multi-site cell.
Okay, wow. So you're telling me, so it used to be that people were trying to get more bits, essentially in roughly the same footprint, the same size, by just adding threshold voltage states. But the more they do that, there's a cost of latency and endurance. And so SK Hynix here is saying, wait a minute, let's split it back out and actually sort of have two transistors essentially. One is like
they just kind of take the same transistor and they just like literally break it in half. Now, you don't want to put two separate transistors because that would double the
Right.
footprint. So they just
Yes.
kind of broke it in half. Yeah.
Amazing. And so just by breaking it in half, they're able to go back down to only needing 6 sort of states in each, and then they can just multiply them together.
Yeah, and you get 36 states, and you can just like blank out a couple of them on either side, and you get 32 states, and each side has to deal with only 6 threshold voltages. So you can imagine if they move around a little bit, it's okay.
Sure.
You know?
Amazing. Is there, there's got to be some sort of trade-off. Was it a little bit bigger area, or what's the trade-off?
No. So I don't know about how reliable this thing is. I don't really know because I don't know how this looks at scale. Actually, if you look at the original paper, it's actually the cell is slightly smaller because the way these NAND transistors are implemented are that they are actually concentric rings. They are not the kind of transistors you typically see in digital devices or whatever. They are basically the silicon channel is in the middle, and you've got like the gate and the charge trap layer is all concentric rings. That's how they are. So this is usually circular. What these guys did was they made it oval. Instead of like having a constant diameter, they made it like 1.2 on one side and 0.8 on the other. So it became like an oval, and then they cut it in half. So it's actually technically about a few percent smaller, but considering that they spaced apart a little bit, maybe I think it's the same size, essentially. They made sure the footprint remains the same. Otherwise, you lose density.
Yeah. Well, then that is like a true innovation that's non-obvious, right? Where usually there's a trade-off, like, oh, if you go this direction, here are the trade-offs, But this is amazing where it sounds like just with this clever idea, they don't have to, in fact, they get better latency and better endurance and the same footprint.
Yeah.
So that's pretty amazing.
That is, and an enormous amount of data density. Now, to be fair, they've been working on this a few years. They call it like 4D 2.0 NAND technology. So if you look that up with SK Hynix, you'll find it there. So they've been working on it for a while now. They have presented at other conferences before. It's literally the first time I ran into it, and I thought it's a really neat. I thought it's a neat way of solving the threshold voltage states problem by just like breaking it up and multiplying them together. I think it's unique.
And so you think it could potentially disrupt the SSD market?
Yes. Thank you for bringing me back to that one. Yeah, I think it can, because you're breaking the fundamental trade-off that you have to deal with as you go to higher level NAND cells. So if you go from quad level, which is what we use currently, and mind you, the current SanDisk quad level cell gives you 256 terabytes to a drive. Okay, it's like 256 terabytes. It's actually more dense than the best hard disks you can buy today, like spinning rust disks. SSDs are actually have more capacity with quad level cells that you can even imagine. Now, with Penta-level cells, you're talking about double that, or maybe we can get 1 terabyte per drive. And in the era of video generation and storing infinite photographs, I mean, you can look up like graphs of how data storage requirements have exploded since the generative AI era. And for all that, we need extraordinary amounts of storage. And devices like this are going to be very important. And typically, going to such dense devices has always had a endurance and latency trade-off. Now, if SK Hynix can increase the data density while improving endurance and latency, that's a big deal. Everybody's going to want this piece of hardware.
Absolutely. And yes, great timing, like you said, with the Gen AI era. I just cringe when I'm making Sora videos with my kids for fun at how many we generate. And they have them, so I can access them still. You'd think that they would say, hey, this is expensive, so you only get this video for 30 days, but it's still there. So yes, we need more bits cheaper than ever.
Yes, indeed. All right. So maybe I should do one more, and that should be enough, because otherwise it's just going to get too technical for anyone to listen to the rest of this podcast. And I want to mention one interesting little thing that Intel presented on GaN-on-Silicon chiplets. And this is also something that Intel has been working on for a few years, and they call it DR GaN. Sounds like Dr. GaN is a nice way to remember it. It has something to do with drivers with GaN. And let me explain. So the fundamental problem with GaN is that you can't make P-channel devices on it. You just don't have a PMOS device. That's a big pain, because without PMOS devices, you can't make half the biasing circuits that is required to drive these things on and off or whatever, or make them switch. So the industry's approach today is to basically make driver chiplets with silicon, and then package it together with GaN transistors that are primarily NMOS transistors. So the problem is that GaN is amazing in terms of the reliability, in amount of power it can handle per unit area, the power density. It has pretty good mobility, much better than silicon at least. So it has all these benefits, but without having a P-channel transistor on it, you can't bias it, you can't do anything on the GaN substrate. So what they do is make a silicon chip and then do all your biasing circuit there, and then connect it on a package. Very wasteful approach. So the idea that Intel has behind doing this is like, hey, why don't we just make the GaN substrate on silicon, and then we'll just how we print like t-shirt patterns or whatever, like how about we just print a little PMOS silicon layer that we can then implant with PMOS transistors. So that's exactly what they do. It's called layer transfer. So they just like stick a silicon wafer with a thin silicon layer that then they peel it off, and it's just stuck there. Silicon is just stuck onto the GaN substrate. And then what you can do is you can put the substrate through, and you can implant it with all this like dopants and all that, create your P-channel transistors, and then finally you go and create your GaN transistors on the same wafer. And there's like an important order here. You have to do the PMOS first, then the GaN. The reason is because processing PMOS transistors and implanting, all that creates heat, and it has to be done in a hot environment, and you don't want to mess around with the GaN transistor and subject it to any heat, because it will start losing reliability, and we don't want that. We want a fresh, brand new GaN transistor. So they usually process it last. So I thought that's an interesting way, and they showed that with a GaN NMOS transistor and the silicon PMOS transistor on the same integrated process, to do everything. They created inverters, they made like NAND devices and multiplexers, all kinds of stuff, and they have like an entire development kit that you can just like drop in all these parts, and it works great. And I haven't even told you the best part about this yet. This entire thing is actually 19 microns thick. It's just 19 micron thick chiplet. And the reason it's so thin is because you can embed it into an organic substrate or a package, like right underneath the GPU or something within the board, so that you can make your power conversion with GaN right where the GPU needs it. So this way you get like all the power conversion with minimum loss through like traces and stuff like that. And so this is called power conversion at load. So these ultra thin chiplets can be made to transfer power at where the exact position where it's required. So it's kind of fancy. So amazing. I thought this is a very unique Dr. GaN, Dr. GaN technology.
It's a Dr. GaN. I love it. So let me zoom out a minute. So GaN, good, but you can't do PMOS. And so silicon today is where they make those driver circuits, and they just have to package those together. And you're saying the first innovation here is basically bringing the silicon PMOS sort of right there on the same chip, like next to the GaN devices, essentially?
Yes.
And so would you consider that like going from 2.5D, if you will, to use the industry vernacular, side by side, to sort of stacking it in a sense, like 3D?
Yeah, but I would like to, be careful about making the distinction, because it's not like you're, packaging it's not like an Intel Foveros it's not like you're putting a silicon chip on top of a GaN chip. It's just that you're taking a GaN on silicon wafer and you're just like putting a layer of silicon paint over it and making a PMOS transistor on it,
It's
So
amazing. Yeah.
you're
So no
bringing the
packaging.
goodness of silicon.
It's built in the same process, built
It's
together.
built in the same process. Yes, you just paint on a layer of silicon and draw your little smiley face of a PMOS transistor, and then you build your GaN transistor next to it.
Nice. And so that's already innovative right there, bringing them together in the same process, building together. But then you're saying also it's thin enough, then it actually enables taking that final device and actually embedding it really close to whichever component actually needs it. It's like a GPU, like the power at load. So it's kind of like there's like sort of two benefits there. It's not only that you can make these in the same process, but then you can bring it as close as possible to where you need it to reduce power loss ultimately.
Yeah, these are also called integrated voltage regulators. So you'll see them called either power at load or integrated voltage regulators. Yeah, so this is very important for that kind of stuff.
Nice. And again, I guess the theme is how can we get as much efficiency, as much compute as possible out of our fixed power that we have access to. So this is again on that theme of innovation to increase power efficiency.
Yeah, on the same note of like bringing two different things together like this, I'll mention another bonus thing I saw at IEDM. So this is a similar thing, but in the RF land, where silicon germanium transistors are really good for like amplifiers. Just like GaN is very good at power and RF, by the way. But then, in order to make switches, they are typically made on silicon on insulator. So CEA Leti, the research institute, actually showed a similar thing that we saw with GaN, where they had a silicon germanium transistor, and then they put a layer of silicon on top, and then they put a silicon on insulator transistor on top of that. So within the same process technology, you have both silicon germanium and SOI, just like how you had GaN and you had PMOS, right? So this is all like, I don't know whether you call it heterogeneous integration, but monolithic heterogeneous integration, something like that.
There you go.
Yeah.
It works for me. Awesome. Fascinating. All right. So listeners, I hope you enjoyed this. This was very technical, but the point here was to let you get a glimpse of the future and what's coming and try to explain it both in a way for people who are less technical to appreciate the benefits. But then if you're technical, you can, Vic will take you as deep as you want. So I hope you enjoyed this, our second episode, and thank you for listening.